Welcome to GeoWatch, your window into the world of semiconductor strategy, global tech trend, and moves of industry giants. I'm Judy Lin, the managing editor at DIGITIMES Asia, where we focus on how the international business strategy of tech giants are impacted by geopolitical dynamics. Recently, we've seen ASML become the leading semiconductor equipment provider in 2023, boasting a monopoly in the EUV market. How has ASML managed to maintain its stronghold of EUV technology amidst fierce competition and geopolitical uncertainties? As we approach the limits of Moore's law, how is ASML tackling the challenges of shrinking chips, particularly with HighNA EUV technology? And what can we anticipate from ASML's strategic partnerships with titans like TSMC, Intel, and Samsung in the Angstrom era? Join us today as we unveil the intricacies of ASML's story. Today, we are privileged to have two experts joining us. First up is Dan Hutchison from Tech Insights, a respected firm known for their expertise in reverse engineering and semiconductor market research. Hello, Dan. Would you like to introduce yourself to the audience?
Thank you. It's an honor to be here. My background is I've been in the industry since the late 70s. I have followed ASML since it was still within Philips and been following it over the many years as part of my job, which has always been, to follow the manufacturing sector of the semiconductor equipment market. At Tech Insights, I'm vice chair. Before that, I owned and ran VLSI Research with a few other stockholders. So that's kind of my background.
Thank you, Dan. Your deep dive into semiconductor and electronics industry really sets the stage for today. And you are such an respected veteran of the industry. We are all eager to hear more from you today. So we are equally privileged to welcome Mark Hadding, the esteemed author of Focus, the ASML Way. Hello, Mark. Could you share a bit about yourself and your journey with ASML that led to the writing of your book?
Hi, Judy. Hi, Dan. Well, thanks. It's an honor to be here. And I'm a financial reporter for the Dutch newspaper NRC. And the last couple of years I spent inside ASML, or at least inside the company, traveled around the world to take a look at all its divisions and facilities and talk extensively to the leadership and write up the story how ASML came to be what it is today. And as a reporter, I also talked to a lot of people inside and outside the company to create an independent and panoramic view of ASML. So that's basically my story.
Thank you, Mark. We really appreciate the book. And you really brought ASML's story to life, breaking down very complex technology concepts for all of us. Right. So let us start with our first question. ASML's business is very much concentrated in Asia. So are other equipment providers. How would the onshore policy of the United States and Europe change that market distribution? Who would like to go first?
I'll go first. So anyway, to remain competitive, ASML has to go where its customers go. It doesn't really have any other choice. It has to be near its customers. And deglobalization, it just decentralizes semiconductor production, the majority of it from its narrow corridor in the Western Pacific. And but besides, if you look at it, they already have customers and they're already where their customers are today and are willing to follow them. Like, look at what TSMC in Arizona, ASML is right there.
So what Dan is saying, that ASML is following its customers, that is a thing that I also have seen when as I was traveling around the world and looked at the facilities of ASML, especially in Arizona. Well, if you look at Arizona, when I traveled there, I also saw that ASML is accommodating its growth of the customers that are rapidly expanding. Not only TSMC, but also Intel, for example, which is building new fabs in Chandler, and ASML has to accommodate that growth as well with all their customer service engineers. But it needs a lot of talent to keep these technical talent to keep these fabs running. And ASML's competing with all the other technology companies for the rare tech talent that is needed for these fabs. And in my opinion, it's not really efficient to just duplicate all these ecosystems. And that's also what you see happening in Asia. That's still the center of all chip manufacturing compared to the European and American expansions. I think Asia is still rapidly expanding even more, which means it will likely be the center of chip manufacturing in the near future.
You know, Mark Glue has actually he said that they're having problems getting talent in Taiwan.
Yes,
and
yes.
I think the talent problem is a problem for everyone. And a lot of like in Europe or the United States, you have this backlash against immigration where we need to be able to immigrate more people in. I think you're absolutely right on that point. The workforce is going to be the big challenge for the industry.
If I can follow up on that, you also see the same problem happening even in the Netherlands, a comparable tiny country, actually without chip manufacturing itself, but with a company like ASML within its borders, it has to accommodate the growth of ASML itself. And what you see happening is there's a restriction, in immigration, for example, and that's kind of holding back ASML and its vast supply chain. And if you look at the long-term line, it's really going to be something that's holding back expansion.
Yes, and especially when geopolitics is getting in the way of ASML's business. China is also building its own supply chain, so they also need talent for their country, right? But on the contrary, is ASML getting helped or getting the driving force for its growth from geopolitics instead?
Sales growth is always going to be driven by chip demand. And the geopolitics just complicates things. It adds friction that diminish efficiency. You know, to Mark's point about, you know, if you have to build all these extra facilities and an entire ecosystem, it just makes everything worse. The one thing about it is, you know, these governments fund these additional facilities. Those facilities have to be equipped, and that creates demand for ASML. And you know, maybe we're in a new world where the utilization of the tools is lower. The problem, though, comes back to Mark's point, and that is if you can't find the workers to run the tools or to repair them, keep them running, a wafer fab is useless.
Well,
Mark, what do you have to think?
Yeah. Well, I think the efficiency in the long term is surely an issue. But if you just mentioned that ASML might actually grow because there's a lot of demand for extra tooling now. But the company, as I experienced it, is tending to focus on the long term and not the short term profit. That's always been in the history of ASML. So I think the long-term problem they see is that, for example, the export controls for China means that the less China gets access to these Western litho tools, the more the Chinese companies are inclined to build their own competitors, even for ASML tools, which means that they might not be able to compete with ASML now or with Nikon even, but in the long term, you see more room for growth and more room for R&D money, for example. And I think ASML biggest fear is by limiting the Chinese technology, that you might even stimulate it in the long term and create an even bigger problem. So a bigger, more efficient, more competitive SMEE, for example.
Yeah, which is it's certainly a challenge for ASML and its dominance. But then the worst part is if you get two competitors that can't be profitable because you have too many competitors in the market, the whole system winnows down. We went through this in the 90s in the equipment industry, where there were too many companies, and the R&D, none of them could really afford the R&D to do the job right. So a lot of them just started fading away and just slowly dying. And it was a death by 1,000 paper cuts, by money paper cuts.
And if I can follow up on that, I think that created room for ASML to grow, actually, because there are a lot of great American companies didn't manage to survive. And I think ASML also, its own supply chain is mostly single sourced even. And if you look at all the big tool makers in the semiconductor industry, they're all like very specialized companies that spend a huge amount of their money on R&D. So it's that's the way this industry operates. And if you're gonna shake it, then it might be less profitable and less efficient after all, I guess. That's my view.
I would say that a lot of the American companies in lithography, they failed because of bad management. And ASML was just fundamentally better managed, which is, what your book shows is it's just a really well managed company.
They had a rough start though, and which meant it was on the brink of collapse for about a decade, until they were a market leader, and they found themselves in a position that they could create enough money to even spend a massive amount of investment on R&D, even during these downturns, and that kind of set them apart. It's a long-term vision. That's why I call the book Focus.
Yes, that leads to our third question. So, how did ASML manage to become the leader of semiconductor equipment industry? So you've just said that by better management and also by devoting more money into research and development. But, it's just became the world's largest fab tool maker in 2023 in terms of revenues. Are there other factors that's been involved in its success?
To kind of follow on Mark's last point, those years in the wilderness where they were starving really made the company stronger. It was their Nietzsche moment, what doesn't kill you makes you stronger. And unlike others, ASML, the thing that I noticed about them early on was they just didn't listen to their customers. They followed my maxim of watching customers to develop a deep understanding, not listening to them, but watching them, and understanding what they really needed and weighing the needs against their own internal core strengths, ASML's core strengths. So, and they did this in particular in the start. I remember with iLine, And at one point they were really paranoid that Samsung might steal their technology and pass it on to Nikon, but Samsung had become really crazy about Samsung, and so I got them to actually, Samsung was very angry at Nikon, and I told them, you should go see Samsung, and they did, and they sort of paid attention to them and started serving them, and they served them better than Nikon did. And then at 157, 193i EUV, in each case, they approached the market very differently, and they were really looking for where the customers' pain points were that they could go solve the problems. And I think that the difference too is that a lot of the companies tried to just sell a tool, and ASML sold solutions, and that was one of the things that's made them so strong. Mark, what's your take on this?
Well, if you look at the company, well, it sells a tool, of course, and actually ASML is a huge company. It's a juggernaut, but it basically is a one-trick pony. It concentrate all its innovative power and all its experience on just one kind of machine, this giant copier. And of course, they build software solutions around them to accommodate that, the measurement equipment. But everybody's on the same page, so to say. There's no distractions from other kinds of machines. So it's a one-trick pony, and it's also delivering tools even at a moment that it's not completely perfect yet. So just to be the first to accommodate its customers, they build new machines. For example, this HighNA machine they just starting to sell. It's a $400 million machine, and it doesn't even work when they ship it. So when they put it together, they just have to figure out and tweak it together with their customers, for example, Intel, to create a tool that has an amount of yield that's enough for it to be economically viable, and that creates like a bond between the customer and ASML. And if the CTO of ASML, the outgoing CTO, Martin van der Brink, he had an expression for that. He always used the phrase, if we wait until it works, then we're already behind. And ASML is always a company that's been driven to catch its deadlines. So they were very much focused on this one tool and on the right time, and building it even and delivering it even when it wasn't finished, and then perfecting it together with its customers. And that, I think that that's basically the secret of their success, their focus.
So ASML has special ties with TSMC, Intel, and Samsung. All three collaborated with them to develop EUV. Are there any lessons that we can learn from that history? Mark, would you like to go first?
Okay. What we can learn from the history is that ASML really needed its customers to take EUV to the next level, to working machine actually, and so they thought up this plan, quite a cunning plan, and they called it Project Musketeer, and the three musketeers of the famous novel. And the first musketeer was Intel, the second one was TSMC, and the third one was Samsung. And these three musketeers had to invest in ASML, and so that created a massive pool of R&D money that could be used to get the EUV machine working. But Intel was actually on a different pace. They invested in ASML because they wanted to create a litho tool that was capable of handling bigger wafers of 450 millimeters, if I'm not wrong. And ASML was kind of reluctant to develop the technology because they had more faith in EUV at the end. And also their other customers, so TSMC and Samsung, rather would see the R&D money spent in EUV instead of 450 millimeters. But Intel insisted, and then ASML's CTO Martin van der Brink kind of called all the musketeers together, and I think it was in at a conference in Silicon Valley, and they kind of surprised the Intel CTO back in the day by saying that, oh, okay, we're not going to follow your path. Not going to follow your lead. So Samsung and TSMC backed out. They wanted to spend their most amount of money in EUV, and it was the point in time, like this pivotal moment, that the Asian chip manufacturers were actually taking the lead from the market leader Intel. So that was I think it was a crucial moment in the history of ASML, but also the entire semiconductor industry. What are your thoughts, Dan?
Well, yeah, I think the technology just becomes so expensive that no one company could go it alone. And as Nvidia's John Chen said, and Don was actually the first R&D person at TSMC when the company was starting up. But anyway, what he said here last year was, no, IC no longer means integrated circuit. Going forward, IC means industry collaboration. I like to call this Chen's Law because I think we're in a new era where collaboration is everything now today in moving the technology together.
It makes sense. And especially if you look where Intel is at now, they have to leapfrog their Asian competitors. And they do. They're going to do it with HighNA, the next generation of EUV, and well, that might be an exciting move.
The interesting thing about your take on the 450 is that I remember there was a time when it was an ASML earnings call, and all of a sudden, Morris Chang steps in and says, "We're going to build a 450 millimeter wafer. We're going to start next year," and it never happened.
No. They spend about I think they spend about a year worth of R&D money at the 450, and then they switched to EUV, and it kind of was that just helped EUV over the tipping point. It was one of the reasons that they actually succeeded in getting this technology economically viable. Otherwise, I think EUV would never have been a thing.
Yeah, and they were hedging their bet with direct write too. They were looking at doing direct write, multi-beam direct write, and that didn't pan out. So they were kind of lucky that EUV came when it did.
Yeah, and you're referring to TSMC.
Yes.
Yeah, and the company that tried that they used for the direct write was also a Dutch company, a Mapper, and which is part of. Well, that's a completely different story. You should read the book for that because direct write was a very crucial part of the American strategy as well. But we'll skip that.
Yeah, and I was always. I've always forecasted that it would never make it. In fact, I had a meeting with ASML when Eric Maurice had just become CEO, and he asked me what I thought, and I says the problem with direct write is it doesn't follow Moore's law.
No.
The whole point of a single exposure is you expose all the pixels at once. So if you shrink the device, you get the advantage of all those additional pixels for free. Where direct write is, if you shrink the device, you now have to write if you double the density, you have to write 4 times as many pixels to do it. And so even though you try to you use chips to make the E-beam system faster, you're fighting it because now you have to write more pixels. And so the throughput of E-beam, they've always been at around 3 wafers an hour, talking about going to 10 for the last 50 years. And that was the big problem with it is the people working on E-beam were just thinking about resolution and the importance of resolution. But doing e-beam in a fab would be like getting the copier out of your office and making everybody hand copy everything. It's essentially what you're doing. That's essentially what you're doing. Go ahead.
It's a very interesting point, as ASML also explained it. Well, their point of e-beam is they use it to actually measure their chips and not create new chips.
Yeah.
And for that, it's a great technology. But
exactly.
There's also
reticles.
It's
essential for reticles. That was I gave a keynote at SPIE in 2018 on this whole topic about e-beam, and I thought I was going to be. I was in front of an e-beam group, and I thought they were going to kick me out, but they didn't. They came up to me and they says, "Man, you just described my whole career." Some of the ones that have been in the industry for 30, 40 years.
So for ASML, e-beam is now kind of the secret sauce for their a new generation of metrology. And right. I think there's also a scientific reason that e-beam has a low throughput, because if you tend to create these structures on a very dense scale, then you have to lower the power, because otherwise the ions somehow interfere. That's what the engineers at ASML explained to me, and that limits the mass production of chips with a direct write. But
it does change it does change the electrical characteristics of the device. Yes. And because the electrons penetrate a lot deeper than photons will.
Yes, indeed. Somehow I find it very curious, because TSMC was not the first to use EUV. It had been using double or triple patterning on DUV for a very long time. But why did it become the leader now? Dan, what's your opinion?
A lot of it was because everyone else was too early. I mean, Intel was way in the lead of developing EUV at the very beginning, but because their processes were 2 generations ahead, they had to decide to go ahead and EUV wasn't ready yet, so they had to, in order to meet their tick-tock plans, they had to go ahead and manufacture with multi-patterning, and then that basically put them behind because it was the wrong decision. And one of my favorite sayings from Bob Noyce, is that you can tell who are the pioneers. They're the ones with the arrows in their back. And that's essentially what happened with Intel, is they had the arrows in their back with EUV. TSMC was able to swoop in and walk away with the real fruits of the technology. And I think the real lesson there is the timing of technology adoption is make or break, and it's a make or break art that really depends on matching, your product with the rest of the industry, because this is a team, technology development today in our industry is a team sport. As I said, IC means industry collaboration. Mark?
Yes, I think it's interesting to see, and I also describe it in my book, how EUV was initiated by for example, Intel, but also Japanese and even Dutch researchers added to the technology. And when push came to shove, Intel was kind of risk averse, too risk averse to adapt EUV in their fabs. And if you compare that to the mindset of, for example, Samsung or TSMC, you see there's a lot more risk taking. They were willing to put more on the line to be the first to use new technology, and somehow that culture really struck the right note at ASML. There was a good mix, especially between during the introduction of EUV, which was a hardship for ASML. They were having a rough time selling it and delivering their promises to Samsung and to TSMC. But when they did, that really created a bond because they both took a risk. And I think it was the former CEO Peter Wenning who said, "Well, I know it's a jump and it's a big jump, but we're jumping together." And that created a kind of cooperative spirit between ASML and, for example, TSMC. And Intel was kind of reluctant. And I think TSMC had the right customers at the right time. There's HiSilicon that actually launched its first semiconductor on EUV. I think it was the Kirin. And then 1 year later, Apple followed with 5 nanometer. And well, I think that was the kind of the perfect timing for the switch of to EUV for TSMC.
Yeah, although to be fair, Intel needed EUV in 2013, and the two just didn't intersect, and that was the problem. Was the timing was all wrong because in 2013 the downtime of the EUV tools was terrible, and the throughputs were also terrible. EUV doesn't really start to make it until 2015, 2016, and that was the and in fact I blame a lot of Intel's failure is on the CEO at the time not saying, "Oh, we're going to pause and wait for EUV to be ready." And instead they tried to Goldberg the whole thing, and it turned out to be a mess, and they couldn't make money at it.
Well, I guess you're totally right that EUV was such a hard problem to tackle, and especially the lights.
TSMC intersected at exactly the right moment, and that was really the advantage. It all goes back to timing.
Yeah.
And sometimes it's random.
Can I just? Oh yeah. Go ahead.
I was going to say Denzel Washington. He says that luck is at the intersection of opportunity and preparedness.
And if you look at what caused most of the delay with EUV, it was the light source that created many headaches at ASML, and they had to it's like this crazy light source that's been generated with hitting a tiny thin droplets with a laser blast 50,000 times a second, and to get it industrialized, it just took years and years and years, and that didn't align well with Intel's timing, and now here we stand.
And now as it gets more difficult to shrink chips, so will HighNA be the the ultimate weapon for Intel to regain their leadership?
Oh, we're going to have to wait on that one. I mean, it's a couple of years into the future, and well, actually, it's next year, I guess. But there's a lot of technology issues in the 2 nanometer and 1.4 nanometer era, and we're going to have to see if they can pull it off and turn it into an advantage. Some of the issues are not just in lithography; they're also in the gate-all-around structures, the leakage problem. There's leakage problems with that. There's also reliability problems. The epitaxial layer is really pretty poor. So really, there's a lot of technical issues to go that are more material systems engineering problems than they are lithography problems. So the solutions, I think we're moving into a period where the solutions will be coming from the Applieds, the Lambs, and the Tokyo Electrons of the world.
So
I don't know. What do you think, Mark? Any opinions on that one?
Well, I think that Intel has to leapfrog or try to leapfrog TSMC. I think it's a daring move, but they have to. And if you look at the technology, there's just one part of Intel's challenge. I think the biggest challenge is not the technology, but the fact that they want to be a foundry business, and they have to create enough footprint or enough size to be economically viable with such huge competitors like Samsung and TSMC. So that adds to the problem of adopting a new technology where they're not as experienced as, for example, TSMC is in EUV. And maybe that explains that TSMC is quite comfortable in doing multi-patterning with EUV for a while and then switching to High-NA after all. Because if you look at ASML, they say that all of their customers that bought into EUV are also going to upgrade to High-NA. They also and if they do that next year or maybe 1 year later, we have to see. But High-NA is going to be a thing.
Yeah, and I think we have to be careful about predicting the failure of individual companies, because it can become a self-fulfilling prediction, where things fail. And I mean, in this case, ASML and Intel, they put their bets on the roulette table, and the ball's spinning and the thing's spinning. We have to see whether it comes up red or black, and you just have to wait for that.
Well, if I can follow up on that, I think it might be interesting not to look at the future, but actually at the past, because the moment Intel signed its High-NA deal, we're talking about the year, I think it was 2017, so it was quite a long time ago. It was a pivotal moment for ASML as well, because they already designed and were preparing for the next generation of EUV, High-NA, before their own machine was actually working, or before they got it economically viable in the fabs. So that deal with Intel was crucial to get ASML at the next point. And I think I totally agree with you. You have to be careful to predict how things are happening, because if Intel wouldn't have invested in High-NA at that time in 2017, ASML could have been in trouble now. Other things have happened.
Yeah. I mean, they could have just basically not had any more technology to keep going down the path. And,
exactly.
And all of a sudden it just stops at EUV because you're stuck with the wavelength. And so the only other thing you can change is the NA.
And what the funny thing about this deal with Intel is it also helped invest ASML, helps ASML invest, for example, in its most important supplier, Zeiss, the German company that provides the optics system. So they built a lab. I think it was an investment of another $1 billion, and that's the lab where they create these incredible flat mirrors. And I've been there too. It's like a James Bond scene. It was mind blowing. And all this technology could have been possible just by this one deal that Intel signed way back in 2017. And now, semiconductor industry takes a couple of years to implement all this new technology into a fab and then get the fab running. So, we should give them a couple of years to catch up. They might.
Yeah.
In Nvidia's GIC, people are surprised to find that its newest chips are actually manufactured in 4 nanometer process, with 4 nanometer process, and integrated into one super chip instead of using 3 nanometer process node. So why is that? And is miniaturization towards 2 nanometer, 1 nanometer, and the 3 or the angstroms level sustainable in terms of economic demand and supply?
I'm surprised. The people are surprised because I don't believe it was because of the cost of 3 nanometer. that it might have a cost advantage or maybe it was too expensive. The first versions of a new node are typically targeted mobile, not data center. And in data center, you need a lot more performance and you don't care about leakage as much. And as I recall, when Nvidia would have been actually locking down that particular node they were going to use, 3 nanometer was still too immature and didn't offer enough benefits. So it wouldn't have made sense for them to jump on it for the same reason of really needing time for the technology to mature and make it to market.
Mark, would you like to add something to that?
Well, it's interesting to see that for me, as kind of a layman in this industry, when I was researching ASML, is that there's quite a massive amount of fraud involved if you talk about all these 3 nanometers and 2 nanometer technologies. Because the actual lines are way further apart than the name suggests. So I think the industry is very much focused on these crazy numbers, and that the real technology under the hood, well, as Dan might know, is completely different. So I wouldn't pay too much attention to one chip that uses another number, for example. It's about the stuff you can do with it. And I think Nvidia has, well, as their numbers prove, they are very much experienced in choosing the right technology.
So, well, no matter what, people are going to need ASML's EUV machines for producing advanced chips. So how long will ASML continue to enjoy a monopoly market in the EUV, in this industry? And are there potential competitors that can threaten their leadership?
I would say yes and no. Without massive government subsidy, no company can challenge ASML's EUV monopoly. And even then, it's questionable if they can pull it off. If you look at the massive size of the co-investment program, that really sort of paints a picture of how difficult it is. And, 5 decades ago, I developed this maxim that the number of unsubsidized competitors a market can sustain is equal to a fifth the total market size divided by the cost to develop a new generation of technology. And then you subtract 1.5 times that cost. Now, in simpler words, basically to attract another competitor in the market, the risk bar must be low enough that there's enough available R&D to support the development of at least 1.5 more tools than exist in the market at that time. And so, and since that, over those 5 decades, that maximum is actually held across 100 or more sub-markets of semiconductor equipment, and really explains the consolidation we saw in lithography from more than 20 suppliers around 1980 to just one in EUV. And today, multiple, when I calculate the cost to develop a new EUV tool from scratch, I come up with a number that's multiple trillions of dollars. And we're talking about some of the largest governments aren't at this level in total GDP. And that's assuming that one can get around all the IP barriers that are in place. So, and to some extent, the interesting thing about it is since one company owns EUV, it levels the geopolitical playing field. So maybe EUV should receive the Nobel Peace Prize because no country can attack any other country unless they have EUV.
But if I can follow up on that, I think EUV is the result of more than 50 years of research. It's blood, sweat, and tears, and fixing a lot of errors. And building it in a lab is just one thing, but ASML accomplished to actually industrialize the technology and keep those systems running for 24/7, and that's a different ball game. And if you look at EUV, it's not just ASML; it's a joint effort of several high-tech companies. So it's including Trumpf, building that crazy laser that hits tin droplets, and also Zeiss that built the optics systems. And Cymer, of course, the American company that created the light source together now with ASML. And if you look at the competitors, they've tried to copy some parts of ASML technology, but it was very hard. And EUV is even harder. And of course, Chinese competitors they try to do the same thing, and Chinese hackers have been in the systems of ASML trying to steal the technology. So ASML is growing up on that part. They have been pretty relaxed, or you could say naive, about their the security of securing their IP, and are adapting to the new situation, because they know their blueprints are very valuable to a lot of other companies. But just copying the blueprints doesn't really help you any further, because you need to copy the total supply chain and also the massive amount of people working at ASML and its culture. I think it's very hard to just carbon copy that and any other part of the world, because it's basically a mixture of Asian and European and US culture. With an extra source of Dutch blindness, and I think that keeps the EUV system an ASML thing for the near future, at least.
Yes, indeed. Well, thank you, Dan and Mark. This is a very, very insightful sharing, and I believe the audience have learned a lot, just like I did. Let me summarize today's takeaways for our audience. Firstly, semiconductor production is decentralizing, shifting from the Western Pacific corridor to meet global demand. ASML faces challenges in expanding facilities and attracting talent, especially in the United States and Europe, while Asia probably will remain the chip manufacturing epicenter. Secondly, ASML's success stemmed from deeply understanding customer needs, fostering innovation through close engineer-customer collaboration, consistent R&D investment, and a modular approach to deliver leading technology solutions at the right timing. And lastly, EUV technology's complexity and cost, dominated by ASML, keeps a very high entry barrier for our competitors. ASML's extensive R&D, collaboration with high-tech firms, and customer networks provide advantages that are very hard to copy. But it also has to be more careful with intellectual property protections, just as Mark had mentioned. Before we wrap up, I would like to encourage you to subscribe to DIGITIMES Asia's Hotspot newsletter service. Receive our free weekly GeoWatch newsletter to keep you abreast of the latest geopolitical news and analysis. Click the link below to subscribe this newsletter. So thank you, Mark and Dan, and thank you, audience, for tuning in today. I'd like to remind everyone to fill out the online survey. You can find the link in the video description or scan the QR code on the screen. Your feedback is very valuable to us, and as a token of our appreciation, please, filling out the survey will grant you a special 10% off promotion code for our premium news. So don't miss your chance to win the prize. Your opinion matters to us. Once again, thank you all for watching this episode of GeoWatch. Don't forget to like, share, comment, and subscribe. I'm your host, Judy. Stay curious and stay tuned. See you next time.